talking about a little bit of stuff that I noticed going on the Chapter 2 test. So these are like solving skills that I would have considered to be like prior Algebra 1 knowledge that I think I saw a little bit of an issue with, not with everybody, but with a lot of people, enough that warrant taking some time and going through and just clarifying some of these issues right now. Okay. So let's say we have a problem like this or something. Okay, this looks similar to things that we would have seen on the previous test, right? Okay, so a couple of issues that I saw repeatedly when students were solving. So the first thing that I saw involves this -3 here. I saw a lot of us doing this. That's incorrect. So the operation going on between the -3 and an absolute value is multiplication. To undo multiplication, we shouldn't be adding. What would we need to do there? Dividing. So I saw that happen a fair bit. So that's not what you want to do. But even if we were to divide -3 here, that's not the first thing that I would recommend doing. Really what we'd want to do first is do the -10. And now when we subtract 10 from both sides of the equation, it really looks like we're subtracting 10 from just two locations, right? Keep in mind, though, that really what we're doing is we're really subtracting 10 from the entire side. Now, addition and subtraction is not distributive, so we can write it like this and everything is fine. The place where I saw the most frequent mistake was now on this next step. So now if we divide -3 to both sides, I saw many of us just do things like this. This is very wrong. Again, remember that what we're really doing when we're adding or subtracting to both sides is we're doing that to the entire side. And multiplication and division is distributive. So really what you want to be thinking about this as is you can't just divide from one location here and one location there. You're dividing by the entire side. Is everybody okay with the distinction there? Okay. Now the right-hand side, the left-hand side is just one term in the numerator and one term in the denominator. The numerator, we just have two things that are being multiplied together, right? So on the left-hand side, the -3's are just going to cancel. But on the left-hand side, the right-hand side, we would have to rewrite this as like -1/3 x plus 4/3. That dividing by -3 needs to distribute to both pieces, because the symbol in between the x and the 4 is not multiplication, but rather addition and subtraction. Is everybody okay with this idea? So I wanted to make sure we took some time and clarified this, because this is an important skill, and it's going to happen over and over and over again here going forward, and we need to make sure that when we're dividing both sides of an equation, really that means dividing each term on that side. So terms are things that are separated by addition and subtraction. So here we have 1, 2 terms. But on the left-hand side, the symbol in between the two things is multiplication. They're just one term. Even though there's that plus sign inside the absolute value is around the plus sign. So we're really thinking of that absolute value of x plus 1 as one thing. Is everybody okay with that? Okay. And again, it's okay that we're a little rusty on some of this stuff. I'm sure at one point when you're doing algebra regularly, you wouldn't have made these mistakes. But it's been a little bit. We didn't do a lot of solving skills in the first chapter, so this is the first time we're running into some of these little hiccups. That's why I want to take some time now and kind of go through this before we get going too much farther forward and start running into more complicated things, because, we don't want to be making, mistakes on these sub-skills, and that becomes the reason why we're getting things wrong on something more complicated. Okay? All right. And I'm going to stop here because those were the main algebraic mistakes that I was seeing. I'm not going to finish solving this problem because I'm not really interested in the solving part of it as much as I am some of these sub-steps where I was seeing the mistakes, and wanted to kind of go back and kind of talk about, like, okay, make sure that when we're doing this that we keep an eye out for this or the other. Okay? All right. Today, we're going to start chapter 3. Which is about systems of linear equations. So when we say linear equations, what we mean is so when we say a linear equation, what we mean is that the variables in that equation all have exponent 1. So we don't have any x squareds or x to the third or square root of x or anything else. We just have like regular old x, y, z, etc. So example, 2x plus y is equal to 5 is a linear equation, because I know the exponent on these variables, when there's nothing written, is really just a 1. Yes? Sure. Okay with that? Just a little reminder of some vocab of what we mean when we say something like that. A system of equations is a group of equations that must be satisfied simultaneously. And this word simultaneously, what do we mean by that? At the same time, yeah. So let's look at an example of a system of equations, of linear equations. So here's an example of a system of linear equations. Usually we put this little curly bracket on the left side of a system to indicate that these are equations that should be looked at simultaneously, that it's not just two separate equations, that these are treated in tandem. Or if there was 3 equations or 4 equations, however many, you put the bracket so it covers all of them. Everybody okay with that? Yeah. Okay. So when we say these must be satisfied simultaneously, what we're talking about is for a solution, right? So for example, 1, 1 is not a solution for this system. Why not? Well, let's show you why not. If I plug 1, well, 1, 1 is really an x and a y, right? If I plug 1 and 1 in for x and y, it does satisfy the first equation, since 2 times 1 plus 3 times 1 is 5. But if I plug 1 and 1 into the second equation, I get 1 plus 2, and that's not equal to 1. Is everybody okay there? However, something like 7 is a solution. And again, let's just demonstrate why we know it's a solution. When I plug 7 in for x and -3 in for y, I get 14 minus 9, which is 5. So the first equation is satisfied. And when I plug 7 and -3 in for the x and y in the second equation, I get 7 minus, which is equal to 1. So both equations are satisfied. Are we okay with what we mean by a solution? Good. Okay. So what we're going to focus on here for the remainder of today is how do we find these solutions? Sound good? Because right now I've just told you this works and this doesn't and shown you why, but I haven't shown you at all like how do you come up with that number or that pair of numbers. And again, that's a perfectly reasonable objection to have, and we're going to answer that right now. So our first method for solving is graphing. So let's say we have the same system that we were just looking at. Okay. So here's our system. And I'm going to ask a question maybe before we even get started going on this. What is the graph, or the idea here? Let's talk about the idea. The idea here is we're going to graph each of these two equations separately. Because each of these equations has an x and a y, we can graph them on the xy axis. And if a pair, an x and a y, satisfies that equation, that means that xy is on the curve for that graph, right? So if the xy satisfies both equations, it means the xy is on both of the graphs. So when we graph both of these together, what are we looking for? I'm not looking for 2 points. I'm looking for the point that lies on both of them, which means I'm looking for where the 2 lines are going to be intersecting. Is everybody okay with that idea? So that's what I'm going to be looking for. So I'm going to graph these 2 and look for their intersection. Now, what shape of graph are these equations going to produce? That should be something you can look at and tell the answer for. An X. Okay, so maybe it's not entirely obvious the way they're currently written. Let's do some rearranging then to make it a little bit more obvious. So when we look at things to graph, typically they start y equals, and then they have the stuff, right? So let's do that rearranging. So we will subtract 2x from both sides, and then divide by 3. I have to divide parts here by 3, so I'm dividing the entire side by 3. Over here, we'll start by subtracting x from both sides, and then dividing both sides by 2. Again, I have to divide the entire side by 2, so both terms get divided by 2. Now if we look at these 2 graphs, what is their shape? What is the shape of them going to be? These should look familiar now. What's that? So if you look at these 2 equations we have now, do they look familiar? Why? Okay, so they're in slope-intercept form, right? What shape of graph does something in a slope-intercept form create? A straight line, right? So each of these is going to be a straight line. Okay. So we're just going to be looking for 2 lines. How many points do we need in order to graph a line? 2 points, right? That was an axiom in your geometry class last year. Points describes a line. So the easiest way to do this is to just pick a value for x and then plug it in to find the corresponding value for y, right? Now we have a bunch of yucky fractions going on here, so I'm going to be a little bit careful about how I'm choosing my x's, because I want to try to pick things so I get a whole number answer, just because it makes the graphing a little bit easier for me. I noticed that since the denominator is 3, when I add these 2 things together, I want the whole, or the numerator, to be a multiple of 3, so it'll reduce down to a whole number. So I notice if x is 1, I have negative 2/3 plus positive 5/3, which is 3/3, or 1. And now I'm going to try, so I've gotten 3/3. I'm going to try now to get something like 9/3 or 6/3 or something like that, okay? So looking at this, there's not an easy way for me to get 6/3, but I can get 9/3 pretty easily. If x is negative 2, negative 2 times 2/3 is, negative 2 times negative 2/3 is positive 4/3. And 5/3 plus 4/3 is 9/3, which reduces to 3. Now, if you gave a decimal, or if you got a fraction, that's not the end of the world, right? Just turn it into a decimal and you can plot the decimal. It just makes it maybe a little bit harder to make sure you've got the graph as accurate as you can. since we're looking for the intersection, accuracy matters a little bit. But if you had graph paper, it's probably not a big deal. This other one. So I notice again, if x is 1, negative 1/2 times 1 plus a half, which gives me 0. And then say if x is 3, negative 1/2 times 3 is negative 3/2. And then plus 1/2 is negative 3/3 or negative 1. So there's that. Yes, Stefan. Stefan. So I picked x to be 1. When I plugged 1 in, negative 2/3 times 1 is negative 2/3. And then plus 5/3 is 3/3, which reduces to 1. Over here, when I pick 1 and plug it in, I have negative 1/2 times 1, which is negative 1/2. And then plus a half is 0. It's because the equations are different. Okay with that? You can pick whatever numbers you want. I tried to pick them so that I didn't get any fractions. Oh, that's what I was going to do. Yes, Bianca.
Okay, so I don't know how to ask this. So basically, we're plugging in the numbers to cancel out like, so we're doing, what are we trying to find for each y? So this one, we just are plugging in random numbers to just get whole numbers.
I tried to pick my x's carefully so I would get whole numbers, but you don't need whole numbers.
So when we're finding the numbers to plug in, we're just getting our y value.
Yes.
Okay, so that has pretty much nothing to do with the x except for the number we're choosing.
Yeah.
Okay.
The x is the independent variable, so you have your freedom of choice there. But the y depends on the x, so you need to plug the x in to find the y.
So we already have our x. Or no?
You're choosing it.
Choosing it, and then we get a y. Okay. So that's just to get our x. Okay.
Yep. Okay. So you notice that I've turned on the graph paper for this because, well, it helps make things a little bit neater. Yeah, if you go to View and you pick the Line Rules option, you can get graph paper on your OneNote if that helps. I'm going to graph this first equation in green, and I'm going to graph the second equation in blue. So let's see, I have 1, 1, and then negative 2, positive 3. Yak. All right, and the other one I have 1, 0, 3, negative 1. Okay, with that? So it looks like my intersection is right about here, right? Everybody agree with that?
Yes.
So if I track that up, I have x equals 7. And I track that over, and I have y equals negative 3. So there's my solution, 7, negative. Is that okay?
Yeah.
Okay. What are some obvious drawbacks to this? Hallie?
I didn't think that. I got like five, maybe.
Okay. So what's that tell us? Well,
Mine's not.
yeah, individually it's not. Like, it's hard to be precise, right? Because this, while perfectly reasonable method, when it comes down to actually drawing this thing and searching for an intersection, it's sometimes difficult to actually have it come out to give you the answer you're supposed to be getting, right? Now, if you had graph paper and a ruler, and the answer is a whole number, you should be able to get it to work. But when you're drawing your own graph all together, and you're not using a ruler, it's sometimes a little bit difficult, right? What's another obvious drawback to this? What if the answer we were supposed to get was 7.12 and it was negative 3.05? Are we going to be able to draw a graph to get that level of precision out? Right? Like if you're not looking for a whole number or, like a half or something, it's very unlikely you're going to be able to find that solution drawing your graph by hand, right? Is everybody okay with that idea? There's one more drawback, and it's a big one. Because these are just a matter of, like, in practical terms, it's going to be a problem. This next one is it creates a problem from a mathematics perspective. What happens if your equations have 3 variables in them? How are you going to graph that if there's an x, y, and a z? Well, you can still graph that. It's going to be a line in 3 dimensions. But, like, there's a way to graph that on a sheet of paper, but it's not easy. And I don't know that it would be practical to find the intersection. But what happens if there's 4 variables? Can you even graph that? We live in a 3-dimensional world. We perceive the world in 3 dimensions. You can't draw something in 4 dimensions. And then it continues. If there's 5 variables or 6 variables or 7 variables, this is not useful for 4 more variables. It's not practical at 3 variables. And it's still a little bit dicey at 2 variables. Now, we can do better in the 2-variable situation because most of the complaints we had were about drawing the graph and making things neat enough and accurate enough, right? Is there a tool that we have at our disposal that doesn't have any issues with accuracy and neatness? The calculator. So let's pull that out and show you how we can do this on the calculator. Okay, so take out your calculator. We'll go ahead and turn it on. If we want to graph something on our calculator, where do we go? The y equals. So let's press that y equals button in the upper left-hand corner. And you'll notice that I've already typed in the 2 equations into my y equals. I put 1 in y1 and 1 in y2. Notice that the y's are already there for us, so all we have to do is type in the right side of our slope-intercept equation. But in order to graph this on our calculator, we have to get the y by itself. So we had to do that rearranging at the beginning if we're going to use our calculators to do this. Remember, to get the fraction command, we press alpha and then y equals and pick the first option. That'll put in the fraction bar for us. It is pretty sick. So take a minute and type these in if you're following along. If you just want to sit and watch, that's okay too. But please do so quietly. And I'll move my little cursor out of the way for you guys. Yeah, it's again, we're just typing these in that we just had done. Ooh.
You're not getting good sleep.
No, it was okay. I'm still catching up from the other night.
What happened the other night? Were you out partying?
Well, my daughter wasn't really sleeping, so.
Party. Yeah. You do one point like take turns, like you take care of one night and you want to take care of one night.
I'm kind of, I guess, but it doesn't, I mean, she was up basically from 11 to 2 on Sunday night, so that was fun.
What do we do after this?
So what do we do after this? So, yes, Andrew. Okay, so you're way far ahead. We're going to talk about what to do next. So just sit tight and we'll catch up with what's going on. Okay, before we hit graph, do me a favor. Up here where it says plot 1, 2, 3, notice how none of mine are highlighted? Check to make sure if any of yours are highlighted. If they are, just move your cursor up onto plot 1, 2, or 3 and press enter to unhighlight it. Andrew, I think that's probably your issue.
Unhighlight it? No, mine are not highlighted.
Okay. So the next thing we're going to do is we need to generate a graph where we can see the intersection. Okay, if the calculator is going to find this intersection, it has to be able to see where they're crossing. So to start to graph this, we're going to press the zoom button, and we're going to use Z standard. So it looks like I can see the intersection. Looks like it's right about here, somewhere over there, right? You can't see it precisely, but the calculator can find it as long as you can tell it's on the screen.
We don't need to find the intersection.
We are going to, but the calculator is going to do that for us.
Yeah, it's like last time, right? Where we
So, hold on a second, guys. Hypothetically, if we did this and you couldn't see the intersection, like they were starting to get close together down here in the lower right-hand corner, but they didn't actually cross, what we would need to do is we need to adjust our window manually. So we need to go further to the right and further down. Everybody agree with that?
Yeah, what? So we put window.
Hold on. Please stop interrupting. Please stop trying to guess what's going to happen next. Okay? So we're in a hypothetical that we could not see the intersection. That instead of them crossing in the lower right-hand corner, we could tell they were getting closer to crossing but hadn't yet crossed. So we would need to go further to the right and further down for us to be able to see the intersection. To do that manually, we're going to press the window button. And to change things to the right, that's the X max. Currently our graph ends at 10 tick marks. We would just need to extend that out to maybe 20 or something. And to go down, that's the Y min. Currently the bottom of our Y-axis ends at -10. We would just change that to something smaller like -20. Now we don't need to do that now because we could see our intersection. We're still just talking hypothetically if we couldn't have seen that intersection. It was getting close, but they hadn't quite met yet. That's what we would do to solve that problem. Everybody okay with that idea? Okay, so we didn't actually do anything here. I just wanted to talk about it. So go ahead and press the graph button if you press the window to return to the graph. And now what we're going to do is we're going to press second and trace. This was the same menu that we used to find the maxes and mins. So from this menu, what command does it look like we're interested in? Intersect. So choose the intersect command. And now it'll return to the graph and ask us for some questions. So notice that I have my cursors popped up here, and the graph is the calculator is asking us to identify the first curve. So the calculator needs to know what two things it's trying to find the intersection of, and then it needs a guess. So right now I can tell if you move your cursor left and right that you're on one of the two lines. So anywhere on that line, go ahead and press enter. And you'll notice now it asks for a second curve, and it's also automatically toggled our cursor down onto the second curve. So go ahead and press enter anywhere on the second curve. And then it asks for a guess. Does the guess really matter? No, just press enter where you're at. It's fine. And a second or so later, it pops up as the intersection is 7, -3. Andrew, did that work for you this time? Okay, show me what's going on.
Sorry.
Okay, so the issue is you have a plus sign way down here.
All right, thank you.
You're welcome. You may. Okay. So easy enough to use the calculator, right? It basically is almost the same as when we did the maxes and mins, the same menus, all that good jazz, basically the same, right? So it should be relatively easy. Okay. Now we've identified that graphing is sometimes has some problems with it, right? So we definitely want some other methods that aren't relying on graphing that would be scalable, that if we had more than 2 variables, it can handle. So let's start talking about those other 2 methods. The first of those 2 methods is going to be called substitution. So we're going to do an example using substitution, using this same system that we had. So the idea with substitution is that we want to pick one of the 2 equations, and then from one of those equations, we're going to pick one of the variables, and we're going to rearrange the equation so that variable is by itself. Now, it does not matter which equation you pick and which variable you pick, but you can make your life much easier by choosing well. So looking at these 2 options, let's call the first one equation A and the second one equation B. Which equation and which variable from that equation would be the easiest one to isolate? I would pick the x from equation B. Why is that one going to be the easiest? Because it's already has no coefficient, so I don't have to do any dividing. The reason I would want to avoid dividing is because division makes fractions. And if I don't have to deal with fractions, I'd rather not. Everybody okay with that plan? So to calculate the x, all I have to do is subtract 2y from both sides. Everybody okay with that? So that's pretty easy. Now what I'm going to do, since I know that x is equal to negative 2y plus 1, I'm going to replace the x in equation A with what x is equal to. So I'm going to rewrite equation A, but instead of x, I'm going to put negative 2y plus 1. And if you look, the equation that I'm left with now has just one type of variable in it. It just has y's. This we can solve for directly. So I'll just distribute my 2 through. And then if I combine my like terms, negative 4y plus 3y is negative y. And then if we subtract 2 from both sides, we get negative y is equal to 3. And if we divide both sides by negative 1, we get y is negative 3. So that's half of our answer, right? That's what y is. How are we going to get x now? Hallie? Yeah, so we can plug y back in for the y in any of the equations that we have above. The place that I would choose is this one, because the x is already by itself. It makes it easiest to solve for x because I don't really have to solve for anything. Now, does it really matter where I plug it into? No. Any of the above would do. So there's my solution. Is everybody okay with that?
Yeah.
The third method we have for solving is called elimination. So let's take that same system that we've been working with. We've been using the same system the whole time because we know what the answer is. So it's nice for us to be able to look at it and know immediately whether we've done things correctly or not, right? So the idea with elimination, what we're trying to do is we're going to multiply one or both of these two equations by some number or numbers. The numbers could be different, so that when we add the two equations together, one of the two variables is going to cancel out. So let's say we're looking to decide to try to eliminate the x's. And I'll call the first equation equation A and the second one equation B. What would I do if I wanted to cancel the x's out? Well, if I multiplied equation 2 by negative 2, that would give me a negative 2x in equation B, right? And if I added 2x and negative 2x, they would cancel out and give me 0. Let's say trying to eliminate the y's. It doesn't really matter which variable we choose to eliminate first. So let's say we wanted to choose to eliminate the y's. What would I want to multiply the equations by to make the y's eliminate? Well, what's a number that 3 and 2 both go into? 6. So let's make one of them 6 and the other one negative 6. So for equation A, I could multiply it by 2. That'll give me 6y. And equation B, I'll multiply by negative 3. That'll give me negative 6y. So when I add them together, the y's would cancel out. Everybody's okay with that idea? It doesn't matter which variable I choose to eliminate first. For the sake of argument, let's just choose the x's because I only have to multiply one equation instead of two. So I'm going to take equation A and add to it -2 times equation B. So that's just a little bit of notation for me to describe what it is I'm about to do. It's not standard. This is just something I've made up. But I think it's important you understand what those symbols mean so that when I can communicate to you what the work is that I'm doing. Everybody's okay with what that means?
Yeah.
Okay. So equation A, I'm just going to recopy. And then -2 times equation B, -2 times x is -2x. -2 times 2y is -4y. And -2 times 1 is -2. I'm then just going to add these down. So 2x plus -2x is 0. 3x plus -4y is -y. And 5 plus -2 is +3. Is everybody okay there? And now I can just finish solving for y. So I'll just divide both sides by -1. So I have y equals -3. That's half of my answer. How am I going to get the other half? I'm going to plug that answer back into either A or B. Which one would you choose? I would plug it into B also. It doesn't matter, but I think that makes life a little bit easier. So there's my, oops, what am I doing here? And then we'll plug in our solution for y. So 2 times -3 is -6. And if I add 6 to both sides, I get 7. So there's my solution again. Is everybody okay with that? Okay. The next question. Do we always get a solution? Why not? Well, let's think back geometrically, okay? So remember we said that solving this system was equivalent to finding the intersection of two lines, right? Everybody remember that from just a few moments ago? Do two lines always intersect? No. When would they not? Great. So we know that parallel lines never intersect. Okay. How can we tell by looking at the equation if two lines are parallel? This was something you talked about in geometry and probably in your Algebra 1 class as well. So you're looking at the equation for a line, the y equals mx plus b. How can we tell that two lines are parallel? Does anybody remember? So when we say the equation for a line, we're talking like y equals mx plus b, right? So what do you mean by the x number? Okay, that's okay. You can guess. I just want it to be like I want to talk through it, right? Like it's you answered. We should talk through it, right? That's okay to guess though. Alexis? It's not the B. Bianca.
The X and Y have the same positive and negative. I think I got it in my brain, I just can't say it.
So what you're looking for is that they have the same slope. Right? If two lines are going up or down by the same amount all the time, they won't ever cross, right? And something else. Something has to be different. What has to be different? The y-intercept. That's the B part. So an example of that would be something like y equals 2x plus 1 and y equals 2x plus 3. These are parallel lines, and because they're parallel lines, we can say there's no solution. Everybody's okay with that idea? Let's look at another example, though. What if they're not already written in slope-intercept form? And let's say that I didn't want to go through the trouble of rewriting them in slope-intercept form. Without rearranging this, is there a way for me to tell if these two lines are parallel or not? Ava, is that a hand? That's okay, you can think. You went from here to here. I didn't know if that was a meek hand raise or not. You can think. Here's a hint. Look at the left-hand sides. Did you notice anything? Bianca? Oh, goodness gracious. I meant for be a 2 there. That makes a big difference. Because it did have a solution before. Now it doesn't. So if you were like, I don't know what you're getting at, Mr. Kulik, and you're like, now it makes sense. That's a good thing. If it still doesn't make sense, we'll talk about what we should be noticing. So here's the idea. I notice that the left-hand side of A is equal to -2 times the left-hand side of B. Oops. But the right-hand side of A is not equal to -B. So LHS and RHS is just abbreviations for left-hand side and right-hand side. We're okay with what I mean by left-hand side and right-hand side? Of the equal sign is what we're referring to. So do you guys see that? How if I take -2 and multiply it by equation B, The left-hand side would be the same as A's, but the right-hand side would be different. Everybody's okay with that? Okay. What if, so the next question then, so we know there can be no solution, right? We just established a way for that to happen. We know that there can be one solution because we've solved things that have one solution. Can there be more than one solution? So think back to geometry. This will be helpful here. Remember that a solution is equivalent to the lines intersecting, right? So maybe a different way to ask this same question would be, can two lines intersect more than once? What do you guys think? Can two lines intersect more than once?
No.
Yes is the correct answer. How would that happen, James? Okay, so lines go straight. So the answer is yes, they can intersect more than once. How is that happening, though? What if I say this is my first line, okay? And this is my second line. If they're the same line, right? Then they would intersect at how many points? Every point, which is infinitely many. So those kind of lines have a name from geometry. We call them coinciding. So coinciding lines, those have the same slope and the same y-intercept. And when we say all their points, we really are talking about having infinitely many solutions. I abbreviate that phrase as IMS because that's too many letters for me to write. So an example would look like this. There's infinitely many solutions. Now it's really easy to tell if the two lines are the same when we've written them in slope-intercept form, right? What if they're not in slope-intercept? Are these two lines the same line? Yes, how can you tell? Okay, what do you mean by that? Okay, so basically what you're saying is that equation B 5 times equation A. Good. There's infinitely many solutions.